A small sphere in a uniform electric field. A small sphere with charge Q is equal to -5 microcoulombs is moving in a uniform electric field that has no y or z component. The only force on the sphere is the force exerted by the electric field. Point A is on the x-axis at x sub A equals -0.4 meters, and point B is at the origin. So x sub B is 0. At point A, the sphere has kinetic energy K sub A equals 8 times 10 to minus 4 joules, and at point B, its kinetic energy is K sub B equals 3 times 10 to minus 4 joules. Part A, what is the potential difference VAB, that is VA minus VB? Which point, A or B, is at higher potential? And part B, what are the magnitude and direction of the electric field? So the first thing I note is that the kinetic energy is decreasing for this negatively charged sphere as it goes from point A to point B. So if we plot this situation, we have a negatively charged sphere which moves from point A at -0.4 meters to point B at 0 meters, and it is losing kinetic energy. So I see that since the kinetic energy at point A is 8 times 10 to minus 4 joules, and kinetic energy at point B is 3 times 10 to minus 4 joules, it is losing kinetic energy moving from XA to XB. So X sub A to X sub B, it is losing kinetic energy. Therefore, the particle, the sphere is velocity is decreasing, so this is a deceleration process. Therefore, the deceleration must be caused by an electrical force. In which direction? The sphere is moving in plus I hat direction and it is decelerating, so the force should be pointing in minus I hat direction. So this must be caused by an electrical force in minus I hat direction. All right, so it is losing its kinetic energy. Therefore, the force is opposing the motion, and the force it feels, the electrical force it feels, is the charge minus Q multiplied by the electric field. If this force is in minus I hat direction, that because of the minus sign here, that implies that the electric field must be in positive I hat direction. So this is in plus I hat direction. All right. So I know that the electrical force is conservative. It's a conservative force. The total energy in this process must be conserved. So we have a change of kinetic energy to potential energy. So how do I think about this situation? The initial mechanical energy of the sphere is its potential energy at point A plus its kinetic energy at point A, and this must be equal to its final mechanical energy because there is no friction, potential energy at point B plus the kinetic energy at point B. There are no dissipative forces. So from this equation, I can read UA minus UB, which is the potential energy difference between points A and B, U sub AB, which is U sub A minus U sub B, its potential energy at point A minus its potential energy at point B. This must be equal to KB minus KA. So its kinetic energy at point B minus its kinetic energy at point A. And this potential energy difference is related to the potential difference. So it is the charge of the sphere Q multiplied by the potential difference between points A and B. So I can see that the potential difference VAB is the difference in kinetic energies K sub B minus K sub A divided by charge of the sphere Q. Okay, so here I'm considering the charge of the sphere Q, which can be negative, which is negative in this case. So don't be fooled by this minus sign here. Here I could have said this is Q times the electric field by definition, but Q is negative. Since Q is negative here, you can see it's minus 5 microcoulombs. Then the force must be, if the force in minus I hat direction implies the electric field is in plus I hat direction. So I note here that Q is negative. Okay, so that would be more consistent if I write it this way. So I can calculate the potential energy, potential difference between points A and B. Potential difference VAB is kinetic energy at point B, which is 3 times 10 to minus 4, minus kinetic energy at point A, 8 times 10 to minus 4 joules, divided by the charge, which is minus 5 microcoulombs, minus 5 times 10 to minus 6 coulombs. So this gives me a potential difference VA minus VB to be plus 100 volts. All right, so that is the answer to part A of the question. What is the potential difference VA minus VB? Which point is at a higher potential? So I can see that point A is at a higher potential. A is at a higher potential. Now, if I, so this was part A. If I look at part B, where I'm supposed to calculate the magnitude and direction of the electric field, the potential difference delta V, which is potential of A with respect to B, VA minus VB, this is related to the electric field between these 2 points as minus the integral from point B to point A, electric field dot product with the displacement dx. So the electric field is in minus I hat direction. So minus E I hat dot product with displacement delta x I hat. So this is minus E x A minus xb. And this is equal to the electric field magnitude E times xb minus xa. So the electric field magnitude is VAB divided by xb minus xa, which means the electric field magnitude is the potential difference, which is related to kinetic energy difference, KB minus KA divided by Q divided by XB minus XA. So that is the magnitude of the electric field. Now, if I plug in the numbers, the potential difference is 100 volts divided by XB minus XA. So XB is 0 minus 0.4 meters. So that gives me E is equal to 250 volts per meter in plus I hat direction. So that is the magnitude and direction of the electric field. So with that, This implies the electric field. So let's show that with blue here. So this implies that I have a positive, some sort of positive charge distribution here, which creates a uniform electric field. All right, so, and some sort of negative charge distribution here. So that the electric field points, the uniform electric field points in plus I hat direction. And the potential difference, so this, since I have a positive charge distribution here, this potential at point A, VA, is greater than VB. Electric field points in plus I hat direction. And the force, the electrical force this sphere will feel is in this direction. That's the electric force, because it's negatively charged and I have a positive charge distribution here. It's moving in plus I hat direction. It's decelerating because the force is pointing in minus I hat direction. Okay, so let's summarize what we did here. We have a small sphere with negative charge, minus 5 microcoulombs, that's moving in a uniform electric field. So it's inside a uniform electric field that has no y or z components. The only force on the sphere is the force exerted by the field, so we don't consider gravitational force, for example. Everything is happening on the x-axis. The motion is from minus 0.4 to 0.0. During this travel, the kinetic energy of the sphere decreases from 8 times 10 to minus 4 to 3 times 10 to minus 4 joules. This implies that the force is in minus I hat direction, causing a negative acceleration. If the force is in minus I hat direction, the charge is negative. That means the electric field must be in positive I hat direction. So we have some sort of positive charge distribution and some sort of negative charge distribution, which creates this uniform electric field pointing from minus 0.4 meters to 0 meters, and the electric force is in minus I hat direction. The electric force is conservative force. There is no dissipative force here. So the total energy must be conserved. Initial mechanical energy, UA plus KA, is final mechanical energy, UB plus KB. The potential energy difference, UAB, is KB minus KA. And the potential energy difference is related to the potential difference with charge. Charge multiplied by potential difference is potential energy by definition. So VAB is KB minus KA over Q, and A is at a higher potential. And the electric field is related to the potential difference. How is it related? Electric field is equal to minus the gradient of the potential. So we can keep this in mind, and we can go from electric field to the potential difference. Delta V is equal to minus the integral from point B to point A, E dot dx, the displacement. The electric field is in minus, is in I hat direction, so we have E I hat with this minus sign here, minus E I hat, dot product delta x I hat. So this gives us E multiplied with xp minus xa. So electric field is kinetic energy difference, kb minus ka, divided by q, which is the potential difference, divided by xp minus xa. If we plug in the numbers, this corresponds to 250 volts per meter in plus I hat direction for electric field, and the potential difference is plus 100 volts.